We've spent the last few days talking about electric forces, which are somewhat like gravitational forces, if you remember. There's a gravitational force that exerted between any two objects with mass. There's an electric force exerted between any two objects with charge. I want to take you back, though, to Physics 20 for a minute and talk about something else, gravitational fields. In order to have a force of gravity between two objects, you needed something to cause the field, and you needed something to experience it. In other words, you could have a gravitational force between you and the Earth. The Earth causes a gravitational field, a curvature of space-time it causes, and then you experience or feel that gravitational field or curvature of space-time. Understand, though, in the absence of you being there, gravity's still there. If you're there, then you experience a force. But if you're not there, there's no force if you're not there, but there's still something there. The Earth's effect on the curvature of space-time hasn't changed. There's still gravity there. Well, how do we quantify that? Well, we call it a gravitational field. We call that influence of gravity when there's nothing being influenced, a gravitational field. Well, we have something similar in electricity as well. If I have a charge rate here, and then I have another charge rate here, and those two objects are nearby each other, then they'll experience an electric force. But if I take away one of those charges, there's still electricity there. How do we quantify that? Well, we call it an electric field, just like the gravitational field that surrounds the Earth. We're going to define an electric field as a region in which an electric force could be experienced. Remember, a force is a push or a pull. In order to have a push or a pull, you need something to be pushed or something to be pulled. You need something to experience the electricity, right? Well, an electric field is a region in which there could be a push or a pull in the electric force if there is something to experience it. If you go back to the gravity analogy for a second, my board marker right now is a certain distance from the Earth, about 1.5 meters above the surface of the Earth. It experiences a gravitational force that's equal to gm1 m2 over r squared. One of the masses being the mass of the board marker, one of the masses being the mass of the Earth. As soon as I take away that board marker, the force is gone. There's no push or pull anymore if there's nothing to be pushed or pulled. But gravity is still there. It's a field that we use to describe that gravity that's still there when the pen is gone. But how do we know that there's a field there? How do we know that gravity is there? Because if I put the pen back, the pen would be influenced. The pen would experience a force. The electric field is that region in which there is an influence. We know there's an influence there because if I put this charge experiencer back, it would experience a force. Understand that there doesn't have to be something to experience it there, but that's how we define the field, is if there was something there, this is what would happen. Does that make sense? All right. Unlike gravity, we have two types of producers. Gravity, we have just a positive mass, right? With electricity, we have, well, we can have a positive charge, or we can have a negative charge. I'm not going to worry about the direction right now of the field, but it's a little bit more confusing in the end than it is for gravity because of those two types of producers. Gravity, one type of mass, electricity, two types of charge. Suffice to say that the shape of the field surrounding a charge looks like the shape of the field surrounding, looks like the gravitational field surrounding an object with mass. It's what we call a radial field. It radiates around this charge. We'll worry about the direction a little bit later on. This is what the shape of it looks like. So electric fields surround electric charges. Electric charges cause this effect. If there's something there to experience this effect, great. If there's nothing there to experience this effect, all right, we still have a field. Okay, right now we have a field. Right now we have a field still there, but now we would also have a force because there's something there to experience that field. We're going to say that the electric fields are vector fields. There's a direction associated with them. You don't know what that direction is yet. You don't know how they affect other charges, but they do, and in a particular direction. Gravity fields are also vector fields. If I put the board marker in the Earth's gravitational field again, it will experience a force in a particular direction, a very particular direction towards the center of the Earth. So gravity is a vector field. There are some examples of scalar fields as well, like a light field or a heat field. It's always cold in this room. I've got my space heater up here behind my desk. If I stand nearby it, I can feel the heat field. I'm influenced by that heat field, but I'm not influenced in a particular direction, up or down or left or right. It just makes me feel better in the presence of this field. It influences me, but not in a particular direction. The heat field is a scalar field, whereas a gravitational field or an electric field, they're vector fields, because when we put an object with mass in a gravitational field or an object with charge in an electric field, then they're not only are they influenced, like I am by this heater up here, but they're influenced in a particular direction. The board marker falls every single time. The charge moves left or right every single time. Now fields will exist as long as you have something to cause them. Right? This is a producer. We'll make it a negative producer this time as opposed to a positive producer like we had last time. The field will exist around it no matter what, whether you have an experiencer or not. As long as you have something to cause it, you've got a field. A force, on the other hand, you need something to produce it and something to experience it. Let's go back to a positive producer. That field goes around that positive producer like this, but you also need something over here, a positive or a negative charge, to experience it. So a force, you need to produce, you need something to cause it and something to feel it. To have a field, all you need is something to produce it. Now let's pay attention to the direction here. We're going to define the direction in two different ways. We can define the direction of the gravitational field. We're not going to write this down because you did this in Physics 20, but we're just going to compare it to the electric field. The gravitational field, we can define, number one, as the direction that an object with mass, like a board marker, will move when placed in the field. Listen carefully to that. The direction that an object with mass will move when placed in the field. So let's put the board marker in the field. If I let it go, which way will it move? Downward. So that means the gravitational field is downward, the direction that the board marker would move when placed in the field. We can define it as the way that the object with mass will move, but we can also define it as toward the producer. The Earth is the producer, right? The Earth is what causes the field. The field line points toward the producer. Well, we can define electric field in a similar way, not the way that an object with mass will move when placed in the field, but rather the way that an object with positive charge would move if placed in the field. So if the Earth is a big charge and the board marker is a positive charge, and I let it go, it will fall, and if it falls towards it, that means the electric field would be pointing downwards. The direction that a positive charge would move if it was placed in the field. Remember, if it's not there, that's okay. It doesn't have to be there. The field's still there. We're just saying this is the way that it's pointing because this is the way that a positive particle would move if it was there. Right? I take away this board marker from the Earth's gravitational field. Gravity still points down. We know that, right? Why? Well, because if there was a board marker there, it would move downward. If there was a positive charge there, it would move in the direction of the field. Now, why don't we choose a negative charge? Why don't we choose a negative charge? It's completely arbitrary. It could be defined as the way that a negative charge moves when placed in the field. It just isn't. We have to pick one charge or the other. And I guess we're optimists. We pick the positive charge. We don't want to be negative people, so let's pick the positive charge. The way that a positive charge moves when placed in the field. Well, just like gravity is defined as the way that the mass moves when placed in the field and toward the producer, we're going to define electric field the second way is toward the negative or away from a positive. Toward the negative or away from the positive. Let's draw a couple pictures here. A couple independent pictures. That's why I have the line drawn in the middle so you can tell that they're not meant to affect each other. Let's make one of them a positive charge, and let's make one of them a negative charge. Let's make this a little positive experiencer, something feeling the field out here. Let's make this a negative. And similarly over here, let's make this positive, and let's make this negative. Let's worry about the force on the positive first, because that's the way we define the electric field, right? Direction of force on a positive particle. I've got a positive particle there experiencing this electric field caused by the big positive. Which way is the force? Which way is the force on this positive particle right here? Left or right? To the left. It's repelled by that positive, right? All right. We define the direction of the electric field as the way that a positive particle would experience a force. That means the field is going to point this way, in the direction of the force, which is away from the positive. We can draw all the other field lines as well, away from the positive. Does that make sense? Positive particle experiences a force to the left, therefore the field is defined as being to the left at that spot, away from the positive. Now let's do it over here. Let's look at the positive over here. Which way is the force on this positive? To the positive and negative attract each other, right? So this positive experiences a force to the right. All right? Experiences a force to the right. Which way is the field? The field is the way that a positive particle would move when placed in the field. So the field is to the right, or toward the negative. Remember this phrase, please. I'm positive the force is with the field. I'm positive the force is with the field. Take a look at this second diagram up here. Got it? Everybody got it? Second diagram. Which direction is the electric force? To the Jack? Yeah, so it's to the right. Which direction is the electric field? To the right. Are you sure? Yes, you are.
Yeah.
Yes? Yes? No, the answer is I'm positive. I'm positive the force is with the field. If it's a positive particle, the force is with the field. Does that make sense? Okay, which direction is the force over here? Ariel, which direction is the force on this one? To the left. Which direction is the field? Are you sure? Are you sure? Jack, help her out here. Positive. I'm positive the force is with the field. The force on a positive particle will always be with the field. Got it? That's just a little way to remember that positive particle, force is in the same direction as the field. I'm positive the force is with the field. Okay, what about the negative over here? What about the negative particle right here? Which way is the force on that guy? It's kind of inward, isn't it? All right, it's toward the positive. Negative and positive attract each other. Look at the force here. The force is opposite to the field. Do we have to change the direction of the field at that point? Do we make the field inward over here? No. The quote is not, I'm negative, the force is with the field. The quote is, I'm positive, the force is with the field. A negative particle would experience a force opposite to the field. So if the field is outward, the force is inward. Similarly over here, we have a field inward toward the producer. The force must be outward. Should the force be outward here? Yes. Negative is repelled by negative, right? So positive particle experiences force with the field. Are you sure? And positive, the force is with the field. A negative particle experiences a force against the field, or opposite to the field. Let's draw a few diagrams here. Let's make this a positive. Listen, to have an electric field there, we don't need something to experience the field, do we? But if we did have something to experience the field, we'd like it to be a positive particle out here, because that would remind us that, oh, the field must point outward away from this positive producer. We know that it points outward because that positive would experience a force to the right, away from the positive producer. Positives repel each other. And if the force is to the right, well, then that must mean the field is to the right. Because if it's a positive particle, the force is with the field. Let's make a negative over here. Here we got a negative particle. Let's put a little positive experiencer in there. Which way is the force on that positive experiencer? To the left. It's attracted to it, right? If the force is to the left on a positive particle, well, then the field is to the left. Because if on a positive particle, the force is in the same direction as the field. Right, Zach? A positive force is with the field. If I'm negative, it's not. But if I'm positive, the force is against the field. Force is with the field. Okay, let's take a look at these. These two diagrams see two charges that are not independent of one another. We got a positive and we got a negative. The field goes away from the positive here. Goes away from the positive. Well, the field also goes toward the negative, right? Well, these field lines end up, whoops, almost threw that one wrong. These field lines end up joining up. I'm going to draw these a different color just so you can see what I'm doing here. These field lines join up. When field lines join up, we get a force of attraction. Remember that. Sometimes you're going to see a diagram that you don't recognize, the shape of it. If the field lines join up in the diagram, there's a force of attraction. If they don't join up, then it's not attraction. You'll see that in the second picture here. Let's label this one positive and positive. Let's draw these field lines going all around it here. Doesn't matter how many we draw. See these field lines coming towards each other like this? They actually repel each other like this. When the field lines don't join up, and you can see here that they don't join up, then we get a force of repulsion. What if I draw this picture? What if I draw this picture? Let's make this positive. Let's make this, I don't know. Let's draw field lines like this. I'm not even going to draw the direction of the field lines. Just draw the shape of the field lines. What type of particle do you got right here? How do you know? How do you know? Yeah, it's repulsion, and then the field lines don't join up. Sometimes you get a question like this, right? Where it's not just, here's a positive, what do the field lines look like? Sometimes you get a problem where it says, here's the field lines, what are the charges, right? Let's draw one more. Let's make this one, here's two charges. Here's the field lines. What do you know already about these two charges? What do you know about them right now? Somebody said it. They're opposite charges. You don't know which one is positive, which one is negative, right? Let's say we put one field line direction there, just one. Do we now know what the charges are? Do we know what both of them are? Yes. What's the one on the right? How do you know it's positive? Okay, the field lines go away from it. Good. That means that these ones will be positive as well, right? Which means that this one over here has got to be negative. You can also tell this is negative because the field lines join up, and when we have the field lines joining up, it's going to be a force of attraction, therefore it's going to be opposite charges. Does that make sense? Good. Good. Let's do this last little thing, and then we'll give you a little break, and then we'll come back to this, okay? Here's an electric field. This is what we call a uniform electric field. Okay, what's it caused by? Whatever, doesn't matter. It's a uniform electric field, meaning it's the same strength throughout. Does that make sense? It's not varying in strength. Okay, if it's this many newtons per coulomb, let's say, that's the unit, by the way, for electric field, newtons per coulomb. If it's X newtons per coulomb in one spot, it's X newtons per coulomb in the other spot. Let's put a charge in here. Let's put a positive charge in here. Let's put it at rest, though. Let's just place it in there, not moving, just right there. Not moving at all. What's the direction of the electric force? Let's say VI is equal to 0 meters per second. What's the direction of the electric force on this positive particle? What is it? It's downward, right? How do we know the direction of the electric force is downward? Because of the arrows? Well, that's the field downward, right? How do you know the force is downward? It's a positive particle, right? In a positive particle, the force is with the field, right? Are you sure? Are you sure, Jack? Positive. The force is with the field. All right, let's do another one here. Let's this time put our positive particle initially moving this way, initially moving to the right. Which way is the force on this positive particle now that it was moving to the right? Trez, which way is the force on it now? Sorry? I'm sorry, I didn't hear that. Away from the particle. The field is away from the particle, the field that's produced by it. But what's the force on this particle as a result of this black field here? Yeah, downward. Doesn't matter which way the particle is moving, the force is with the field. By the way, which way is this particle going to go as a result of that? Yeah. Yeah, somewhere in between. Actually follows a curved path like this. Do you know what the shape of that would be? What is it, Dylan? It's a parabola, yeah. It's like projectile motion physics 20, remember that? If you launch an object off the edge of a building, it experiences gravity, it follows a parabola. This is like launching a charge off the edge of a building, experiences a force, except it's not gravity, it's an electric force, follows a parabola. It's really a projectile motion problem. What if what about this one? What if we had a positive particle initially moving upwards like this? Like this. Which way is the force acting on it? Right? Downward. Are you sure? Positive force is with the field. Right? What's going to happen in this case right here? Situation number one, this charged particle is going to speed up downward. What's going to happen in situation number two? It's going to follow a parabolic path like projectile motion. What's going to happen in situation number three? If it was moving upward but there's a downward force, it's going to slow down. It's going to continue moving upwards, but it's going to slow down. Does that make sense? In all three cases, though, the force is with the field. What if I made all three of those negative particles? The force would be upwards now, right? If I made them all negative particles, the force would be up in diagram one. It would speed up in the upward direction. Diagram number two, it would follow a parabola like this if it was a negative particle. Diagram number three, the force would be upward opposite to the field, and it would now speed up because it would be moving up with a force upward, causing it to gain speed. Let's deal with this mathematically now. You see three equations up on the board that you should recognize. The first one is my gravitational force equation. We learned that in Physics 20. We reviewed it earlier on in this unit. The force of gravity between two objects is g, the constant, times m1 times m2 over r squared. There is an analogous electrical equation. We've done that already as well. Do you remember what it was? The equation for the electric force between two charges that's real similar to this one. Not gm1 m2 over r squared, but rather the electric force is k q1 q2 over r squared, charge 1 charge 2 over meters squared, distance squared. All right, what's that second equation? We haven't done that this year, but you saw in Physics 20. What does little g stand for? Yeah, it's the gravitational field strength. In the field strength, a certain distance away from whatever is causing the field is gm over r squared. M would be the mass of whatever is causing the gravitational field. R would be the distance from the center of whatever is causing the gravitational field. Anybody want to take a stab at what the analogous electric field equation is for a producer when you have information about what is causing the field? It's not G is equal to gm over r squared. Rather, it's E is equal to kq over r squared. Good. Now be careful here. This Q is the charge of the producer. You may be given the charge of the experiencer. That's not what we want to use. We want to use the charge of the producer in this equation. R would stand for the distance from the center of the producer. And that's going to be measured in meters. The units, by the way, for this, it's going to seem a little bit weird to have these units. It's newtons per coulomb. Where does that come from? Let's take a look up here for a second here. K is Newton meter squared per coulomb squared. Q is coulombs. R squared on the bottom is meters squared. Things start canceling out like crazy here. One of the coulombs cancels, and I'm left with newtons per coulomb. So the units for this would be newtons per coulomb. What's that bottom equation here on the left-hand side? That's my experiencer equation, right? When I know something about the gravitational field experienced by something. The middle equation, talking about the board marker and the Earth again. If I know something about the Earth, then I would use this equation to find the gravitational field. If I know something about the board marker, what experiences the field, then I would use this equation to find the field strength. You know something about the producer, use the middle one. You know something about the experiencer, use the bottom one. What do you think the analogous electric field equation is? If you know something about the charge that experiences the electric field. Christian? What do you think it would be? Mason, what do you think the electric field experiencer equation would be? Not G is equal to F over M, but rather G is equal to, or E is equal to F over Q. The electric force over the charge. Now this is the charge of the experiencer, not the charge of the producer. And this is the force experienced. And that's going to be measured in newtons. And once again, because it's force over charge, we get newtons per coulomb for the electric field strength. Now, if it's me, this is the way the equations appear on your data sheet. If it's me, I'm going to add something to it. Absolute value signs around those. I find that the way they do things on your data sheet, by not putting absolute value signs around those, is a little bit inconsistent. Yeah, I'm going to put absolute value signs around those to be consistent. If you forget to put those in, it's okay as long as you still do things the way that I do it. What's not okay, you don't want to forget the little vector sign because you're going to get it mixed up with energy if you do that. But if you forget the absolute value signs, that's not a huge deal. I'm going to put them in there to be correct. If you miss it, you're probably still going to get it right. It's just not technically consistent. So when you want to find the force between two charges, there you go. When you want to find the electric field, it's one of these two equations. Depends on what you have information about. When you have information about what causes the field, it's this one. When you have information about what experiences the field, it's the bottom. Here's example number 1. It says determine the electric field strength and the direction 50 centimeters to the right of a sphere that has this negative charge. I'm going to circle that. I'm going to circle this. And I'm going to circle this. Just little things that can lead me to silly mistakes, right? Negative charge, centimeters rather than meters, microcoulombs rather than coulombs. Let's draw this out so it makes a little bit more sense. Here's a negative charge that produces the field. Its value is 25 microcoulombs. We want to find the field strength out here. Is this a producer or experiencer? You want to find the field strength right here, take 50 centimeters or 0.500 meters to the right of this charge. This charge cannot possibly experience this field because this charge isn't in the right place. If this charge is going to experience this field, then this charge needs to be right here. Does that make sense? If you're going to experience a temperature right now of 30 degrees Celsius, you need to be in Mexico, not here. Okay? In order to experience something, you need to be where it is. This charge is not in the right place to experience this field. Therefore, it can't be an experiencer, it must be a producer. Let's use the producer equation then to find the field strength at that point. Let's say KQ over R squared. That's 8.99 times 10 to the 9 times Q, which is, careful here, it's 25 times 10 to the negative 6. Notice I've dropped the sign of the charge, as I always do when I sub charges into equations. It's negative, but I dropped it. R is 0.500 meters. We got to square that, though. 8.9, oh, I think we can do this one right now. 8.99 times 10 to the 9 times 25 times 10 to the negative 6. This one works out to be, I think, doable in our heads. Why? Because 0.5 squared is 0.25, which is 25 times 10 to the negative 4. And cancel out the 25s. And I get 8.99 times 10 to the 3. Is it 8.99 times 10 to the 5? Oh, no. Got this wrong somewhere. Is it, what's the answer? 8.99 times 10 to the 5? Okay. I was on the right track, got the wrong exponent. What are the units? Units per coulomb, right? Units per coulomb. Well, we just found the magnitude, but what about the direction? The equation will never give us the direction, all right? We can find the direction some other way. What is it? Read, look at this diagram up here. At this point right here, if I was to put a positive there, there's not a positive there. There isn't. But if I was to put one there, which way would it move? Towards it? Yeah. So that means the field is to the left. Because a positive particle, if it was there, would experience a force with the field. So we don't need the equation to tell us that. We just draw a picture and remember that little quote, I'm positive the force is with the field, in order to figure that out. All right, I'd like to have a look at worksheet number 8 right now, questions 1 to 4 for now. There is going to be more, but for now, it's just questions 1 to 4. Have a look up here. We want to find not the strength of these. I'm just going to go through finding the direction of questions 1 and 2. 1 and 2. So number 1, it says that we have a positive charge right here, and we want to find the field to the right of the positive charge. Which way does the field point to the right of a positive charge? Away from the positive. The field is to the right. You can find the strength of that by using KQ over R squared, but the direction is just found by saying it's away from the positive producer. What about number 2? The strength and direction to the right of a negative charge, negative 2 coulomb. Okay, we're going to find the field over here. Which way is it point? To the left, toward the negative. You can think of it in 2 ways. Away from the positive toward the negative, or you can think of it as, well, what if I put a positive there? It would move to the right. What if I put a positive right there? It would move to the left. Does that make sense? So try calculating the strengths of those, and then also doing question 3 and 4, the strength and the direction. One more example here. Let's do example number 2. So there's a positive 1 nanocoulomb, whatever a nanocoulomb is. If you don't know that, just look on your data sheet. In the middle of your data sheet, top part of it, middle. Experiences a force to the left. What's the magnitude and direction of the electric field at that point with 100 nanocoulomb experiences with force here? So here's a 100 nanocoulomb charge. The field strength here, or the force, I should say, is to the left. Is that a producer or experiencer? Is that producing a field, or is that experiencing a field? Yeah, if it's experiencing a force, it's experiencing a field as well. So we're going to use the experiencer equation. We're going to say E is equal to F over Q. That's going to be, notice I put the absolute value signs there on it because I don't want to worry about direction there with that equation. F is 4.00 times 10 negative 5 newtons. Now, don't worry about the direction. Q is 100 nanocoulombs, or 100 times 10 to the minus 9 coulombs. Again, we're not going to worry about the direction here. We do the division there. We get 4 times 10 to the minus 5 divided by 100 nanocoulombs. We get a value of 400. 400 newtons per coulomb. Now, what about the direction? How many people say the direction of that field is left? How many people say to the right? Emily, why did you say to the left? The force is to the left, and it's a positive particle, and, well, if it's a positive particle and the force is to the left, then the field must be to the left because I'm positive the force is with the field. So the field is to the left as well. Here's your homework for tonight. You do have practice question set number 10. In addition to that, you have the worksheet that you were just working on. If I get to the right spot here. Worksheet number 8 all the way up to question number 7 now. Worksheet number 8, questions 1 to 7.